In this lesson, we're going to talk about our delta connected systems. So we are going to look at the relationship between your line as well as your phase quantities on your delta connections. The first slide is showing the relationship between our voltages, that is your line to line voltage. I know I keep saying line voltage, but please remember it's a line to line voltage, okay? It's between two lines or two phases. And our phase quantities. So in the triangle that you see, it's actually your delta connection where you've got your A, B, and C phases. And then you can see your VA, your VB, and your VC. And also showing are your line-to-line voltages, VAB, VBC, and VCA. At the bottom, I'm now breaking it up into small sections for us. So at the bottom here, I've just shown now between A and B phase, and I'm saying that my VA is actually the same as my VAB, which would also be the same as your VB in this case. So right there at the right hand side, I've drawn in that my VA is equal to my VAB. Then if I show you across my C phase, between C and A, in fact, you can see that I've got also VA is equal to VCA. So I can deduce that my line voltage is equal to my phase voltage in this case. Then looking again at the first one that I drew in, my VB can be seen to be the same as my VBC. I've just drawn that one in. And from the first one I drew in, which is also equal to VAB. Then the last point is for my VC. And for my VC, I again look right at the bottom. It will be the same as VBC. And then on the right hand side, it will be the same as VCA. So all we're saying here that no matter where you are looking onto the system, you find that your line and your phase voltages are all the same throughout. While the currents are acting in a different manner. So if I have to look at the current in the case where I have now, you will see that at phase A, you've got two incoming currents and one outgoing. So therefore, I can say that my IA minus the outgoing one plus the other incoming one will equal to 0. So that is IA minus IAB plus ICA equals 0, which is therefore IA is equal to IAB minus ICA. Now I want to take this and draw it into a phasor diagram for us so that we can be able to get the exact value of IA. So here is a phasor diagram at the bottom where I've drawn in my IAB in the same direction it was in there. And then I drew in my IBC and my ICA at 120 degrees from this point. So after I'm drawing this phasor diagram, I then take across minus ICA, and there it is in the red dotted line. Once I've drawn in my minus ICA, I can see now I've got a relationship between what I wrote in Kirchhoff's law of IA is equal to IAB minus ICA. I then draw in a resultant, which will be my IA current, of course. And if that was to be in a parallelogram, you could clearly see how that becomes my resultant current. After drawing in the parallelogram, I can draw in an intersector between my IAB and my negative ICA in the smaller dotted line that I've just drawn in there, and then I label everything within my parallelogram. Now I can wanting to deduce exactly what my IA value equals to. So the first thing that I do is I say, all right, I've got OB, which is the same as my IA, and I can say that is parallel to my AC. Because it's parallel to my AC, it means that it is bisected into two or in half. Okay, so OB is equal to 2OM, and therefore my OM actually equals to IAB cos 30. That's why I wanted to draw this thing, the bisector, in so that I can have a 90-degree angle and we can relate to a 90-degree angle triangle, because that's where we have our sines and we have our cosines and we have our hypotenuse, our adjacents, and then our opposite sides. Okay, so my OM would be equal to IAB cos 30. My cos 30 is the same as saying is square root of 3 over 2. Hence, I get my OM to be equal to square root of 3 over 2 IAB. If I then replace the OM by OB, it will be twice the OM, which will be twice the square root of 3 over 2 IAB. The 2's will cancel out, and I'm left with IA is equal to square root of 3 IAB at an angle of 30. 30 how? The angle of 30 is clearly shown here that it's behind my IAB, so it lags my phase current. So my line to line current, which is my IA in this case, is going to be the same as my square root of 3 I phase, and it will lag my I phase by 30 degrees. I want to explain why my IA is a line, whereas my IAB, ICA, and IBC are phase currents, okay? Because in the voltages, it was something else. Now, if you look at this, between A and B, that's actually one phase of your delta system, okay? That's why IAB is your phase voltage. Whereas this IA is directly going to my A phase. That's why it's my line current. So it's the opposite the way that they've named the currents to the voltages. Then this slide is exactly what we had on the previous one, but I'm showing this between A and B as well as between B and C. And I can see that at the point of B, I will have IB minus IBC plus IAB equals to 0. Therefore, my IB is equal to IBC minus IAB. I take the above again and I draw a phasor diagram. All right, so my phasor diagram is exactly the way that it was on the previous one. But now what do? I'm now looking at IBC, okay? And since I'm looking at IBC, I know I must bring across my negative IAB. I bring that across, I draw in a parallelogram, and there I can deduce that IB is equal to square root of 3 IBC. And then on the last one, I'm showing at point C where I've got IC minus ICA plus IBC equals to 0. I take that one again and I say, therefore, my IC is equal to ICA minus IBC. At the bottom, I draw the phasor diagram. When I draw that phasor, I can then say, okay, where is my ICA point? I go to where my ICA point is, and I say, okay, that's where I'm going to draw. So I need to bring across my negative IBC. I put in my parallelogram and I draw my resultant, which would be my IC. Then to follow that my IC is equal to the square root of 3 ICA. So in this slide, I'm showing the relationship between your delta connected systems of your voltages and your currents, all right? And in brackets, I've said it's a positive phase sequence, which I'll be explaining in the next slides. So here you can clearly see that you've got your ICA, you've got your IC, and you first have your voltages, which are being lagged by your currents, okay? And then you've got your line currents, which are further lagging your phase currents. What I want us to note then is the following, that the voltage that you may be given in a question at any point in time should be your line voltage unless they state otherwise. How do they state otherwise? Well, we first need to recognize how our line voltages are named. Your line voltages will be between two lines. So it's irregardless if it's a delta connected system or a star connected system. If it's between two phases, not just a phase and a neutral, but between two phases, your line voltage will always be having the two phases as part of the name. So it's VAB, VBC, or VCA. It's a line voltage. If it's not given in that manner, it means, for example, you have a star connected system and they say it's a VA, okay? Then you will know that your VA is not your line voltage, but what is it in this case? It becomes your phase voltage, and therefore you must know that you're given a phase voltage. If you have to change it into a line, you do so accordingly. Then the second part is that your your voltage is always the reference point unless they state otherwise. So they will say take V whatever as your reference point. And then the last part is that your reference point is always at 0 degrees unless it's stated otherwise. So if they say it's at a specific angle, you can't assume it's 0. But if they don't give you an angle, your assumption is it's 0. So you don't have to stick up your hand in a test or an exam and say, I don't have an angle. You must remember, if the angle is not given to you, it's 0. This slide just summarizes what we learned in this point, bringing it into perspective again of your delta and your star connected supply connections. Okay. Then we talk about your positive and your negative phase sequences for the first time. So on our left-hand side, we have what we call our positive phase sequence. How do I know it's a positive? Number one, it gets named as ABC, is another name for a positive phase sequence. So for me to be sure that when I do my drawings, I'm really on a positive phase sequence, I must look at this little dot that you must always draw for yourself and put in a big plus sign like I've done, the red plus sign. And then your axis must rotate in an anti-clockwise direction, just like I've shown with that arrow there beneath ABC. So when I rotate my axis through that dot over there, it must go through that dot, A phase first, followed by B phase, then followed by your C phase. Then on my right hand side, I have what I call a negative phase sequence, all right? So a negative phase sequence is now saying that it cannot follow an ABC through that dot, but it follows a CBA, sometimes named an ACB. Is actually the same thing, all right? So when I now rotate the right hand axis through that dot, I can see that my A point goes through, followed by my C point, followed by my B point. If I had to go again, it would be followed by my A point. So you can see how I can still have from ACB back to a CBA point. You just keep rotating it around that same point and you can see how the letters will follow each other eventually. As the last slide on this lesson, I just want us to note this that is now different. That in a positive phase sequence, okay, which is your ABC phase sequence, your line voltages, line to line voltage, will lead your corresponding phase voltage by 30 degrees. Whereas in a negative phase sequence, your line to line voltage will be lagging your corresponding phase voltages by another 30 degrees. Thank you.